All right. Well, it is noon time, and I am going to get started. So today's session is actually zoomed because one student had a very special circumstance that it would not be easy for her to take this class in person, but she'll be here with us in all the exams. So don't worry about the but she's going to take the exam offline on online and it's not fair to the rest of us. Nope, she'll be here to take that class, to take the exam also in person. All right, so we are resuming our discussion of all the set notations, and so we are on difference last time, because we worked out a few examples, right? So do you want me to go over more examples, or do you think that is sufficient to make sure that you understand all the concepts? So we're good? Okay. I'm not sure what you mean by that. Speak up, please. Huh? More examples. Okay. So we can use more examples. Well, let's try to get empty set into our examples. Okay. So we're gonna try something like, oh, I'm just too lazy. So we'll do, oh, I forgot that this is all in a VI key binding, so I can do this, which is cool. Okay, we'll put an empty set here, an empty set here, and also an empty set here. And then we'll get rid of all the answers, and then you guys can tell me what the answers are supposed to be. We'll start with the intersection. Oh, okay. I just answered the question that I was about to ask you. I was this symbol is what is this symbol representing? Yes. So what is the result of ABC as elements in a set intersecting with the empty set? It would be the empty set. In other words, I'm asking you what is common between a set that has A, B, and C in it and a set that has nothing in it. The answer is nothing, okay? Or a set that has nothing in it. The next one, okay? So next one is, so this time I can ask you, what is this symbol representing? Union, very good. So what is the union of a set that has ABC in it and a set that has nothing in it? Yes. So A, B, and C would be the elements of the set as a result of the union operator. That is correct. So let me go ahead and type that answer in. A, B, and C are here. And to emphasize that ordering does not matter, I'm just going to do it that way. Okay. And then the last one is what is the set of ABC minus, or the difference between the set that has ABC in it and the set that has nothing in it. So this one does require you to remember a little bit of which side is the exclusion. Yes, it will be the same as just ABC. That is correct, because even though we are taking a byte out of the set, the byte is empty. We're taking nothing out of the set on the left-hand side of this minus. Yep. Hmm? No, it's on at least one side because it's an OR. It's a logical OR. When we look at the actual expression of what union is, it is a logical OR. It's not an exclusive OR. Yep. All right. Very good. Um, do we need more examples? Okay. So one thing you guys can do is to come up with your own examples. Okay, so if you're not sure, you come up with a certain example and you say, I'm not really sure about this one, then go ahead and try to answer the question. Mute desktop 2. All right. And I'm going to start the recorder again. No, it is still recording. Okay. I don't know exactly what is going on.
I think it recorded my screen. I don't know. Still recording earlier.
All right. So it should be recording now. I can hear the other student on my headset. So that's, I'm not talking to myself. No, that doesn't mean that I do not talk to myself. It simply means that in this particular incident, I wasn't talking to myself. I mean, this is a class about logic, right? So it is important to understand what that statement actually means. Okay, does it mean that? Hmm? Okay, so if you want the best quote about talking to oneself, I think the best one is from Megatron, as in the Transformers. And this one is from Beast Wars, which is before most of you were born. Okay, so Megatron in the Beast Wars, as an animal, he was a T-Rex. So one day, he was as usual talking to himself, scheming, planning, and all that stuff. And then one of his minions, walked by and go like, "Hey, Megatron, how come you always talk to yourself?" And his answer was, "Well, I have a penchant of having intelligent conversations." And then he gave a disgust looks to his minion, who did not even register what that meant. That was the best quote ever on the topic of having a conversation with yourself. Yes, or in Megatron's voice, yes. All right. So getting back to this one, and I think we are recording. Yep. Okay. Go ahead and ask your question. Can you see on the, oh, you mean the earlier examples? MT said, yep. And yep, that is correct. So the best reference of all of this is the notation that we were using, that we were looking at. So this is the how subtraction or difference is defined. So an element or a value is in the difference between x and y if and only if it is in x but not in y, which is actually what you said. Well, x and y cannot imply each other because x and y are sets and they are not Boolean values. You can only have the so as an operator, implication requires the left-hand side and the right-hand side both being Boolean values. Otherwise, it would not make sense. This is a definition. So that means this entire quantified statement is by definition true. Every time you use this symbol here, this is what it means. So it is definitive, which means every time you use this symbol, it means that any element, any value that is in x minus y has to meet this requirement. And anything that meets this requirement has to be in x minus y. It goes in both directions. So if and only if is very strict. If the left-hand side is true, the right-hand side also has to be true. If the right-hand side is true, the left-hand side has to be true. If the left-hand side is false, the right-hand side also has to be false. If the right-hand side is false, the left-hand side also has to be false. So they have to be the same. Hmm. The okay, so in X implies Y, X and Y are both Boolean. They are not the same. So that particular module is the one right before this one. So it's a prerequisite requirement. So let's take a look at that one. So we are looking at implication, which is this symbol here, X implies Y, versus this symbol here, which is X if and only if Y. So that's the truth table of if and only if on the right. You mean here? Yes. It's this is one way to look at if and only if. This is the other way to look at if and only if. So choose the one that works best for you. Yep. Yep. You will if this is the first time you take my classes, you would probably notice that many times I'll give you options. Like this is one way to do it, this is another way to do it, and this is yet another way to do it. And the kind of questions that I cannot answer is when someone asks, so what is the best way to do it? They all work. Choose one of them. Okay. So I just want to kind of let people understand that there are many times there are different ways of doing things. There are different ways of looking at things. None of them is wrong. Just choose the one that works best for you. All right. So are we good on this particular topic? Okay. All right. So now we go back to the definition of difference and go back to our example here. Are there any additional questions about the examples that we have looked at so far? Mm, Well, okay, if you guys don't have questions, I'm gonna make some questions on my own. So I'm gonna say, um, what the hell? Oh, caps lock, typical. Okay, there we go. So if I just say that I have some kind of a set A, and I am going to make a union of with an empty set, can I come to a conclusion at this point? Okay, I shouldn't use question this here. Okay, put a question mark here. So I don't even know what set A has. It can maybe empty. It may have a bazillion items. I don't know. Okay, can I answer this question? Every item in A, same. Okay, so basically the answer is just set A itself. Does that make sense to you? Yes. Oh, for every set A, this is true. Is that what you mean? You mean using a quantifier? Well, this is a little bit harder to use a quantifier, but I can certainly use words to describe it. Okay, for any set A, you mean from the perspective of elements of the operator? Okay, let me see if this is what you meant. Okay, so you're basically saying, we want to use the notation of for all E is in A, if and only if E is in A union with the empty set. Is that what you meant? Okay, yeah, we can do that. But I think the first one is easier to read. Huh? This has nothing to do with programming. This is algebra. Believe it or not, this is algebra. So yeah, but the property has nothing to do with coding. The whole point of this, if you're talking about the actual code, how to implement that, then yes, the for all is translates to actual language constructs. So yes, that is true. But from the perspective of this class, which is focusing more on the theoretical side, this is algebra. You go like, this doesn't look like any algebra that I'm familiar with. Sure, you are. You have already, you know that if x is a value like an integer value, x plus zero is x. So what is the term that we use to describe that zero? It is a constant, but in this case, this constant has a very special property. It is called the identity. So zero is the identity of addition. One is the identity of multiplication. Very good. And as a result, the empty set is the identity of union. Okay. So now, why is that stuff important? Because some of you may need to take a class called abstract algebra. Okay. And it's a fun class to take. I believe it really helps with computer science students, even though in most computer science programs, it is not needed. But I think it is a good class to take. It is called abstract algebra. And in that abstract algebra class here, we are trying to identify really common properties of different systems. Okay, so are you working on Boolean values? Are you working with set values? Are you working with real values, complex numbers, and so on and so forth? As it turns out, there are certain things that are very common between all of these systems. So that's what that class is about. Um, but I'm not going to get too much into that kind of concept, but I want to kind of introduce some of those terms. So for those of you who are curious, you can look it up and learn it by yourself or take that class when you move on to a 4-year university. All right, very good. But since we are talking about identity, let's see if there's another identity that we can spot here. I think there's another one. Okay, so I'm gonna copy and paste here. This one is not needed. What about difference? As it turns out, any set, the difference of any set and the empty set is the original set. Kind of makes sense. All right. So it is spotting and understanding these, what I call boundary conditions that really test what your knowledge of whether you understand the operator or not. All right. So are we ready to move on to the next item? Yes. Hmm. 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 Yeah. But you're taking a bite out of nothing. So what do you get? Nothing. Yeah, exactly. Yep, we had that as an example from the previous class. You mean this one? Yep. This is what X is referencing in the definition. This is what Y is referencing in the definition. So we are looking for everything that is in X but not in Y. Because because we are taking things away from the left-hand side that are found on the left-hand side. On the right-hand side, sorry. Yep. Well, D is not on the left-hand side to begin with. It is of no concern to me. Yes. And Darth Vader would have said, things that are only on the right-hand side but not on the left-hand side do not concern me. As if they're asteroids. If you don't know what I'm talking about, it's time to rewatch, episodes 4, 5, and 6 in that order at the same, not at the same time, but in the sequence. Yes. Huh? Identity. Okay. So I'm gonna put it this way. Okay, I'll put it in a way that is uh, probably a little bit foreign to some people, and but it is probably the best way to put it. Okay, so let me start the tablet because this one is going to be handwritten. Okay, so the whole concept of an identity is something like this. So let's say we have an operator like this. You go like, there's no such operator as a square. Yep, now there is. Okay, so now we say, if you have a value that we call x, okay, so x is just a particular value, and you operate on something, and we'll have the other side being, we'll use another symbol here. Okay, we'll put a little Darth Vader helmet here. Okay, so obviously this is not real. Okay, it is just each one. It's just a symbol. It's a placeholder. X is a placeholder of some kind of a value that the square operator can operate on, and then the Darth Vader is also just another value that can appear on the right hand side of the square operator. Is that okay? Is that abstract enough for you? Okay. If no matter what X is, this always ends up as X here, then Darth Vader, the symbol, is known as an identity with respect to the square operator. That's basically the whole concept of an identity with respect to an operator. So we are used to 0 being an identity with respect to addition, or 1 being an identity of multiplication. Is that okay? All right, cool. But this is kind of a little bit out of the scope of this class. Nonetheless, it is, some kind of, symbology that is commonly used in computer science. It vaguely or loosely connects to the concept of um, overloading operators in C++ programming. Okay, if in your mind you're going like, so that's what it is, then you're getting it. It's kind of like that. So every time you overload, an operator, let's say you overload the operator plus, you also have to quote unquote, you cannot do it in the language. You also can overload 0 to mean whatever the identity of addition is for that type. But you can't do that in C++ because C++ simply does not allow you to overload constants. But you can always define a method called 0 and use 0. Yep. There are some people who use 0 to denote the empty set. So you could do that. Yeah. Yep. Mhm. Is that okay so far? All right. Cool. So any other questions about those 3 operators that we have examples on? Union, intersection, and difference. No questions? All right, so then we're going to move on to the next one. I did make a mistake earlier, so that's why, this may appear to be a little bit different. So this is how we define X is a subset of Y. So once again, this particular statement here is by definition true. Okay, that is how we define the operator that is inside the square portion or inside the rectangle portion. So we say that X is a subset of Y if and only if everything that is in X implies that something is also in Y. Okay, that is the definition of X is a subset of Y. Okay, So it's time to use an example again. Okay, so this time it's going to be a slightly more elaborate example. Let me go here and hmm. Oh, right, because you decide the other side is not scrolled down yet. Okay, all right, so let's take a look at this example. So we're going to say that X has the elements, oh, I don't know, let's say A and B, okay? And let's say, set Y has, A, B, and C in it. And we want to know, whether X is a subset of Y in this case. So now we have to evaluate a bunch of stuff. So now we have to say, okay, what if E equals to A? Well, if E equals to A, E is in X is true, and then implies E is in Y, which is also true. So true implies true is true. So this is true. Is that okay? Let me make it a little bit more explicit. So let me just kind of put parentheses around this and say, okay, that is true to me. Yep. Um, no, it is not from the perspective of elements. It is from the perspective of the set. And typically, you want to look at things from the set on the left-hand side of the operator, because you basically are asking, does the other set has everything that I have? Now, can the other set have more stuff? Yes, but it cannot have less stuff than you have. Because E is a universally quantified, thing. So if I go back to the definition, you can see that this E is universally quantified. In other words, I have to go through the whole process of saying, what if E is this value? Is the statement being quantified true? What if E is this thing here? Is the quantified statement true? And so on. Okay, so say again. Well, let me complete the example and see if that's okay with you. Okay. So what if E is B? In other words, we are just using a different value as E to reevaluate the quantified expression. And is that true? Well, let's see. B as a value, is it in X? Yes. So E in X is true. What about E in Y? Well, E has a value of B is in Y, and so the right-hand side of the implication is also true. True implies true is true, so we are good. Then you go like, what about other things? Okay, what if E is tag? Okay, well, because potentially because it's a universally quantified statement, so E can bind to anything in the entire universe. And at this point, I'm still a part of the universe, so E can bind to tag. So now the question is the quantified expression still true? In other words, E in X implies E in Y. Is that expression still true? Okay, so instead of interpreting what I just asked you intuitively using your language mind or using the language portion of your brain, use the rational part of your brain. Okay, in other words, mechanically evaluate the expression. So how do you mechanically evaluate the expression? Implication has two sides. I have to know the value of the left-hand side and the right-hand side to find out whether the implication is true or not. Okay, so that means I have to evaluate the left-hand side and the right-hand side independently first. E has a value of tag. Tag is in X is not true, okay? Because I am not in the set X. Okay, by the definition of X, I am not a part of it. I'm not an element of set X. Well, I think that should be enough to answer the question because on the left-hand side of the implication, you have a value of false. We're done. And if you're questioning or if you're thinking, why are we done? We are not even evaluating the right-hand side. Well, you might need to review the truth table of implication. Yes, the left-hand side is false. I automatically know the entire implication is true. So you can look at it, you can look at A implies B as not A or B, which is also the reason why I can say if the left-hand side is false, then the whole implication is guaranteed true. Yep. So you can get to the same conclusion once again from multiple perspectives. None of these perspective is more correct than the other one. It's just do you want to look at it from the mechanical perspective as a truth table or the expanded expression of not A or B. Yep. Hmm. We negate the left-hand side and then disjunction with the right-hand side. Yep. So that's, I mean, this is kind of interesting, right? So no matter what things you throw at E, no matter what E binds to, this statement is going to be true because you can throw things like, what about 23? Okay, let's do 23. Okay. And there's no particular reason I choose that number. It just pops up in my head. Okay. So make that 23. It's still the same answer. It is still true. Yes. Say again. The left-hand side is false. So the implication is true. What do you think? Okay. So the question is, in an implication, if we know the left-hand side is false, do we need to worry about the right-hand side? And if we do not, why? Yes, that is correct. But you can also see the answer to that question in the truth table. In other words, we are asking, what if the left-hand side, which is known as x in this truth table, is false? Oh, it doesn't seem like y make a difference at all when x is false. So that is the reason, okay? That is the reason why every time we know x or the left-hand side is false, we don't even worry about the right-hand side. It's like there's no way you can change the outcome of this implication. Yes. Hmm. 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 Nope, nope. Just it's just memorization. Just deal with that table. Or you can also look at it from the perspective of x implies y is the same thing as the negation of x or y. Yeah, the either way works. They're both mechanical ways to get to the same result. Yep. Hmm. Yep. Oh, that is important. The reason why we want to show that no matter what E binds to, the quantified expression, which is this part here, the parenthesized portion, is still true, is telling us that the quantified expression, the entire thing, is always true. Because by definition, okay, if I switch back to here, because by definition, we need this portion to be always true no matter what you throw at it. That is definitive because that is how we define X being a subset of Y. That's why, I want to show you in this concrete example no matter what we use to bind to the variable e, the expression that was being quantified is still true. No matter what you throw at it, this part is still true. So that's why, by definition, in this case, x is a subset of y. Okay, so my recommendation is formulate your thought a little bit for, let this do a little bit longer before you announce it. Okay, so but it's hard to do it in the class. So maybe after class we can have a discussion. All right. And by the way, I will be in my office after class today because I have a meeting at 3:30. So I'll be in my office for a little bit after class. So if you have jotted down some notes, okay, you go like, what about this case here? You can always come to me, after class, and then we can get all of that stuff clarified. Okay. All right. So any other questions about a subset of, using the subset as a notation? So you can see that the subset is kind of like less than or equal to, because it's kind of like less than or equal to, okay? Which means in this case, x is, no matter what set x is, it is always a subset of itself. Okay, let me stay that over here. Okay, so TAC is saying that x is a subset of x is always true, assuming x is a set. And I'm gonna be nice and format that correctly. There we go. But does that make sense to you? Do you think every element in set X is also found in set X? Exactly. It does matter because that's the reason why X is a subset of itself, no matter what X is. What if X is empty? It's still true. Yep. Can you formulate a question again? What if, okay, because the formulation of a question is very important because that is how your brain is using or trying its best to use the concept that you have learned in order to come up with a scenario where you go like, okay, what about this particular scenario? But in order to describe that scenario, you're already exercising the things that you have been learning. Just let me know when you are ready for that, okay? And since we are using Zoom, I suppose we can use a whiteboard in Zoom to do this, but I can always just take a piece of paper. Yep. Um, okay, so you are asking about the inverted A symbol and also the inverted E, but in different axes, right? So the first one is called a universal quantifier, and the second one is called an existential quantifier. Yeah. Mhm. All right. Any other questions? All righty. So if there are no questions, we are going to move on. Okay. So I know someone is working on a problem, and you can do that after class too if you want to. Okay. So there's no need to do it during class, but you can capture your thought as much as you can at this point. So the next one is X is a proper subset of Y. So the first one is just subset. The second one is proper subset, which is also described here with proper in italic because that is an important word. So what does it mean when we say X as a set is a proper subset of Y, which is also a set? First of all, X has to be a subset of Y first, okay? But on top of that, there's a conjunction here. In addition, there has to be one thing, at least one thing, that is found in Y that is not found in X. Now, there's another way to write that, okay, and I can talk about it, after this whole thing, and then, but I just want us to focus on the definition of proper subset. Yep. Yes. Yep. You can do that. There are several ways to express the same thing. You can also express it as X is a subset of Y, but the union of the two does not equal to X. Okay. You can also say X is a subset of Y, but Y minus X is not empty. So there are several ways to say exactly the same thing. Yep. Sure, but I cannot remember all of the alternatives. I can only remember the one that I talked about. Okay, so we'll start with that one. So X is a subset of Y. Okay, I'm gonna do it in proper mathematical notation the whole way. Okay, so put this in parentheses and close it first. So right, left arrow, which is if and only if. So now we go like, okay, what other way can we say this? And why is it complaining? Let me scroll up. Oh, right, left arrow. It's left, right arrow, not right, left. It's left, right arrow, which is if and only if. All right. So there are two things. The one thing that we always kind of refer to is just X is a subset of Y. Okay, that's always a requirement. But then on top of that, we can add something else so that we can describe is a proper subset of. So the one thing, okay, I'm trying to remember what you guys said a little bit earlier, but I remember the two things that I said. So the one thing that I said was Y minus X is not empty. So we will just say not equal to the empty set. Okay, that's one way to put it. Because what this means is there is something in Y that is not found in X. Okay, the first part says when I say X is a subset of Y, it means everything in X can be found in Y, but that's all it says. After the conjunction, okay, after the conjunction, then we are also saying that there has to be something, at least one thing, that is in Y but not in X. So I'm using the difference in this case. Okay, that's one way to do it. The other way to do it is to use the union. Okay, so now we say Y union with X does not equal to X. Yep. Well, if Y union X does not equal to X, that means there are some elements that are only found in Y. It implies that. Because if everything in X is also found in Y, then the union between X and Y would have been just X. Yep. You are running a diff and you're making sure the diff is non-empty. So the question is, how do you express that the diff is non-empty? So the first one is using the diff approach. You have a file, you have another file, you're using the diff, and you're looking for things that are only found in Y. But it is not sufficient by itself without the conjunction to define is a proper subset of, because you first have to say everything in X is also in Y. You have to we have to preface it with the first statement, which is everything in X is also found in Y. Okay. Is any of these not making sense to you? Yes, go ahead. It's it's all the things that can be found in Y or found in X. Yep. Hmm. Because the union is kind of derived from OR because the opening is on top, and the OR symbol also has the opening on top. Hmm. Yep, yep. Well, all of these is being recorded, okay? And I'm going to put all of these examples into the notes too, into the actual module itself. So, all of these will be captured. Anything else? Are there anything else you want to ask about is a proper subset of? Okay, go ahead. Mm, it says everything in X can also be found in Y. So that's what X is a subset of Y mean, is everything in X is also in Y. The first one is this one. So it's basically saying, when you look at things that are in Y but not in X, it is not nothing. Right. And that has to be non-empty. There has to be at least one thing that we can find in Y but not in X. Yep. Hmm. Yeah, that is correct. A set being a proper subset of itself is always false. Yep. Hmm. All right. So I can, okay, friend, I can, you're just gonna copy and paste this one and just, do a little tweak here. It's always false, which is, just what we said. All right. So are we good with a proper subset of? Yep. All right. So I shall preach again the importance of reading ahead of time and writing in your own notes how things are defined. This one is saying that X is a subset of. This one is saying whether X is a proper subset of. That's okay. It happens because this one has an extra word, this one has an extra line. But you can look at subset of as less than or equal to, and proper subset of as just less than. So you're excluding the equal to. Hmm. Yep, go ahead. Then X is a proper subset of Y. But if X is already a proper subset of Y, it implies that X is also a subset of Y or equal to. Yep. Yep, go ahead. Okay. Which part are we referencing? Are we looking at the examples or are we looking at the definitions in the module? Okay, so go ahead. So okay, let me take a look at your screen. So you're looking at uh-huh. Oh, okay, I see. I was using the wrong symbol. Okay. So this one here is without the bar below, which is supposed to be there. So let me fix that first. Okay, so I just need to look for the contextual information. And this is a subset of, okay. Thank you. That was good catch. Good catch there. And this is how I fix the whole thing. And we're looking at subset of, okay, I'm too lazy to search for that myself. Alrighty. So that's okay. Yep. This is a subset EQ. 23. Oh, okay. It's because it just says for all. Okay, there we go. Thank you. All right. Thank you. Yeah, this is the problem of me, trying to update the material every single time I teach a class. Hmm? I'm not sure whether that's a good thing or a bad thing. Well, these days it's not just Chat GPT. I'm waiting for the whole thing to get baked. There's also Deep Seek. How many people have heard about Deep Seek? Okay, I'm glad. Okay, I'm glad that you guys are at least having a pulse on the industry. Um, this morning I was reading an article that Toyota is asking Amazon because they use AWS, for their website. They're asking AWS to see whether DeepSeek can be available as a service so they can use it. I go like, okay. I'm just gonna pose a few questions. Okay, one, who publishes DeepSeek? Two, what is the country behind the organization? Three, what would be the intention of making something like this powerful and useful to be public domain? Well, open source, not the same as public domain, but nonetheless available for free to the rest of the world. I'll just post those three questions and let you guys figure out what you think are the answers to those questions. And after you answer those three questions, then you can also answer the question of should I use DeepSeek? So everything is posed in the form of a question. I am not expressing any political view. Yes. Well, that would be a test for you guys to conduct. Then you can come to your own conclusion. Or, because it's also capable of generating images, right? So you can now ask, DeepSeek to generate a humorous picture of the fearless leader of China and see what happens. I have not done it. I have not seen any, pictures or images of someone trying it, but I'm curious to see what would come up. Do we see a panda? Do we see it would just say, authorization in progress. Please wait. All right, so now it is fully baked and this mistake is fixed, and so is this one. Thank you for letting me know. And if you have a GitHub account, you can also, do your fixing and then do a pull request, and then I can take a look at your edit. If it's all good, I will just kind of let it in. I think that is a interesting model, of teaching material because you can not only fix things that are erroneous in my slide, you can also add additional examples. It's like, okay, I think these examples can also help to illustrate the concept. Add them in. Okay. All right. So are we good so far with all the way up to X is a proper subset of Y? All right. So the next one, which I just fixed, thanks to Alina, is basically the definition of what if we have a set to describe and it has an infinite number of members. And I'll give you an example of that later. So that is when we use this notation. The notation uses the curly braces or just braces to mean that, okay, I am describing memberships in a set. That's what the curly braces are for. And then this part reads as each element E in this set has to satisfy this requirement, which is P of E, which is just a predicate. Yep. No, that's just so that we can easily differentiate. Are we talking about R as some other in some other context, or are we talking about the set of all real numbers? Yep. Okay. So this is definitional or definitive, which means every time you see something like this, which has open curly braces, some symbol, a vertical bar, which is also read as such that, and a closed curly brace with some kind of conditional statement here, that means exactly this thing here. If and only if P of E is true. So E is an element of this particular set if and only if P of E, the predicate, returns a value of true. Okay, so it's time to look at an example. Okay, so let's go ahead and take a look at an example here. And this notation is typically used to describe a set that has an infinite number of elements, such as the set of all even numbers. So let's go ahead and try to describe the set of even numbers. Okay, so that's kind of the notation here. So I will start with the notation and then we'll go back and kind of look at what it actually means. So we can start with n such that n is an element of the set of all integers. The set of integers is also using this kind of funky symbol here. It looks like a Z, but it looks kind of funky with two bars and in it. So that means it is in the set of all integers and close paren. And on top, now we have to say, since we're talking about even numbers, so we also have to say n mod 2 equals to 0. Okay, so this is one of many ways to express I want to describe a set of all even integers. All right, so you look at this notation and you go like, what does that mean? Well, okay, let's give this set a name so that we can reference the name in the alternative notation that is basically the same thing. So if E is defined this way, then the alternative and slightly more cumbersome, but I think it's a more clear way to define it, is the same thing as this. Is the same as saying this part here. For everything under the sun, E, oops, E is in E. Okay, I guess E is not a, let's use N instead, because otherwise I have to spell out, uppercase or lowercase, so N is good. Okay, so N is in E. Once again, if and only if, okay, left, right arrow, if and only if, and then I just copy the same equation as above, and I can just copy and paste, but I'm just going to type here, and is an element in the set of all integers, and, whoops, just pressed the wrong key. I apologize for for all the unnecessary scrolling, and then we just have the usual n mod 2 equals to 0. Yep, okay. All right, so let's digest what we have just presented here. This is the short form. This is, the first part is the short form, which is also what most people use. The question is, what does it mean? Well, it means exactly the same thing as the second form, which is saying for everything in the entire universe, that thing is in the set E and is in E, if and only if, which means the true false of the two sides of the if and only if has to match. If one side is false, the other side has to be false. If one side is true, the other side also has to be true. So if and only if what? N is an element of the set of all integers. So that means 1.5 automatically disqualifies on this side, and therefore it also disqualifies on the other side. Okay, so let's say it's 2. Okay, 2 is an element of the set of all integers. So now we have an and. We also need to make sure that 2 mod 2 is a 0, which is true. So true and true is true. If this side is true, okay, if the right hand side of the if and only if is true, then the left hand side also has to be true, which means 2 has to be an element of set E by the definition, by the way we define it. Is that okay? So it's a notational kind of thing. The notation here, this notation, this part here is more common. People tend to use that notation. But what that really means is the same thing as the notation that is described below using the universally quantifier. So is that okay? And this is also a good example to illustrate why P of E is just a placeholder. Because P of E, okay, let me show you where the context is for P of E. This P of E here, that is just a placeholder for a Boolean expression that basically describes what qualifies to be a member of the set. Okay, so P of E is just a placeholder of an expression that involves the use of E. In our example, the P of E basically expands to just this expression here. So basically the predicate that needs to be true for all members inside set E is the highlighted portion. Yep. Mhm. I'm not sure how that relates. It is, it's basically something that has to be true for all members in the set. And everything that meets that requirement has to be in the set. Everything that does not meet the requirement cannot be in the set. Are we do okay so far with the notations? Yes. Yes. When you want to describe, what makes a particular value a member of the set. Yep. In other words, it describes membership. Are we doing okay? Yep. You mean uppercase E? So uppercase E is just the name of a set that by definition is what we have here. So that I don't have to use this entire thing in place of this E over here. It just makes it easier to read. The set of all integers and n mod 2 is a 0, which means n divided by 2 has a remainder of 0. Yep, because the original idea is I want to describe a set of all even integers. Yep. All right, so is this notation okay? All right. Now, if you have some question about it, but you cannot quite formulate the question at that point, you can always, kind of jot down in your own notes, okay? Put a few question marks down, mark the time right now, which is 1:06, so that if you want to reestablish the context in which you go like, okay, I had a question at that time in the class, but now I cannot remember. Go back to exactly the same time, and then you can try to remember, what was my question about, this material at that time. So I think the recorded lecture can be a useful resource, but it is not a replacement of not being in class. So even the remote student is actually in class right now. She's actually live with us. If she asks questions, I can hear that. All right. Do we have any questions about this notation, which is just describing, what makes a member of a particular set? No questions? All right. And now we are down to a few easy ones and then a few really difficult ones. This is an easy one. The bar notation is not absolute value. It is asking how many things are in the set. And you can see that, not exactly, but close. That's why I use the word similar, okay? So the cardinality of a set is similar to the number of items in the set. You go like But why is it only similar and not exactly? Because later on, in the Aleph Null module, we'll be talking about comparing a set that has an infinite number of elements to another set that also has an infinite number of elements. And then we say, are they the same or are they not the same? You go like, it doesn't make sense. Okay. You cannot compare infinity to infinity. That is true. But you can compare the cardinality of a set that has an infinite number of elements to the cardinality of another set that also has an infinite number of elements. Yes, yes, yep. It has to do with the countability of a set. That's Aleph Null. The module talks about that. Now, to give you a preview of the kind of stuff that we're going to deal with in that particular module, I'll just kind of post the questions without answering. Okay. So the question is this. Okay, I'll give you the question and then, but I won't give you the answer until we get to that point. So this is the set of all integers, and I'm asking. Okay, this question mark here is not assertive. It is not saying that it is equal to. It's asking, are they the same? So now the question is, what cardinality are we talking about on the next item? This is the set of all natural numbers. So now I'm comparing the cardinality of the set of all integers against the cardinality of the set of a set of all natural numbers. Integers include negative values like -2, -6, and so on. Natural numbers can start with 0, it can start with 1, depending on how you were taught. Okay, in this class, we start with 0. So the natural answer is no, they cannot be equal to each other because there are things in the set of all integers that is not found in the set of natural numbers, like -1. But as it turns out, the equality holds. So we'll examine why that is the case because it does not make sense, and yet by the time we talk about functions, then you go like, oh, okay, I guess it does make sense. Yep. Yes. So when you use the word map to each other, you're already talking about the concept of functions. In fact, the way you describe it, you're describing what we call a bijection, which goes in both directions. Yep. But you're way ahead of the class. But I'm glad that you're using those concepts. But for the rest of the class, we kind of have to wait a little bit until we get to why there's an equality here. Okay, so this is the beginning of a kind of interesting, but yet it's complex, but yet also not too complex if you look at the definition. Yep. Um, well, that's the thing. The set of natural numbers is actually a proper subset of the set of all integers, but yet they have the same cardinality. That is the one thing that a lot of people cannot reconcile because they would think if there are things over here but not here, doesn't mean that it's less than. The answer is no, not by the way we define cardinality. So, or the way we define the equivalency of cardinality. So we'll get to that later. Okay, this is kind of funky, but we'll get to it. All right, so the next one is easy. This is just a notational kind of thing. So a lot of times, instead of writing this, which is kind of long and clumsy, we just use this notation here. We just say for each element E in set X, P of E has to be true, which is just a notational thing, because otherwise we're going to have to go through the longer definition, which is saying for every E in the entire universe, E is an element of X implies P of E, which basically this part here, okay, let me use my mouse pointer here. So this part here, from about here to here, is a filtering mechanism because all it's saying is, oh, for things that are not even in X, we'll just by default make the implication true so they don't matter anymore. So it's a filtering mechanism, okay? So we'll use this notation quite often, in this class. The next one is also a notational thing for the existential quantifier. We can say there exists one thing E in X such that P of E is true. Now, there exists means there's at least one, so there can be multiple, but we should be able to find at least one thing in X such that P of E is true, which is what the boxed portion is trying to say. But the long form of this one is only saying that for everything, there exists one thing in the entire universe, okay? At least one thing in the entire universe, such that that thing is an element of X and P of E is also true at the same time. So the first one, which is the boxed version, is just a shorthand for the longer version here. Is that okay? This is purely a notational kind of thing just to make things a little bit easier to type. The next one, and we barely, yep. It's just an easier way to express something like this, so that it's more clear that every E that we're considering is already pre-filtered to be an element of a set X. Yep. All right, so I'm going to give you an example, and I'll ask you guys whether it is true or not. Okay, so we'll switch to the Joplin again. So this expression goes like this. I will say for every element E in the empty set, we just have an expression here that is always false. So the question is this quantified expression always true or always false? Okay, what do you think? So at first glance, this does not make sense at all. Yes, the answer is true, okay? So at first glance, this doesn't seem to make sense at all. It's like um, by default, the expression itself does not even depend on E. It is just giving me a straight answer of false. It's kind of like somebody asks you something, and as soon as the other person opens the mouth, you just say nope. Okay, and yet the quantified expression as a whole, okay, if you look at this entire thing, it is actually true. It's like, what? Doesn't make sense. Well, it actually makes perfect sense once you translate this back to the long format. Okay, so let's go ahead and take a look at the long format of this particular statement. Because the long format is simply saying, oh, okay, for everything in the entire universe, okay, E in empty set implies the second portion. So implies is right arrow. And then the second portion is just false. Okay, that's basically the long format. Okay, so you look at the long format, and then are you now convinced that the quantified expression has to be true? Because the left-hand side of the implication is always false. Nothing is in an empty set. Yes, because on if the so the way I remember is just everything. If the left-hand side of an implication is false, the implication is true. And because the empty set has nothing, so when you ask, is this in the empty set? The answer is always no, always false. So if the left-hand side of the implication is guaranteed false, then the implication is always guaranteed true, which means, oh, yes, no matter what you choose in the entire universe as variable E, this statement is always true. And as a result, the quantified expression is also always true. Are we good? Yes? Huh? The zero is coming from here. Yeah, yes, because the zero is what P of E is. P of E is simply saying, I don't even care what E we are looking at. False. That's all it's saying. It's always false, 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 false. I have to watch out for my hand gesture. Yes. But I think this is still okay. I think Richard Nixon is still okay. As long as I don't say I'm not a crook, I'm okay. Yes. Hmm? P of E is zero, is false. The upside down E is for all. For every E in the entire universe, blah, blah, blah. P of E is true. So P of E in this case is false. Yeah. So this is an example that is in the format of this. We're changing P of E to just false. Yep. So P of E is a placeholder for a Boolean expression. In the example, that Boolean expression just turns out to be the false as a constant. I don't even care what E is. You first and then you. Go ahead. If it does not even matter because we don't get to evaluate it. Because if P of E is 1, if this is 1 and this is also 1, false implies true is always true as well. So it does not even matter. Go ahead. Okay. Okay. So the question is, why do we, what, whether it is reasonable or whether it makes sense, in some people mind to define implication as not X or Y. X implies Y can be defined as not X or Y. In my mind, this is how I remember X implies Y. I don't even use the other operators to define implication. Oh, well, for Boolean operators, the best way is to use the truth table to look at how an operator is defined. Yep. Which also means, if that's kind of one thing for you. So okay, before we leave, I know we are a little bit over time already, but Ryan is always late anyway, so I can use a little bit of time. Yes, I just use a universal quantifier. Uh-huh. Yep. So, but let me address that first, and I'll get to your question. Okay. Um, I do not give you guys any study guide. Okay. For those of you who have taken my classes before, that is true because only you can prepare your own study guide, which means after every single class, you basically look through your notes, look through the module, and then you work on your study guide just a little bit after every single class. You just go like, okay, what is noteworthy? Okay, so in your case, you do not like the expansion of not X or Y. So now you want to go like, okay, I need to put some extra effort to memorize the truth table. And the truth table itself may be important in the exam because you don't want to rely on your memory. So that should be on your study guide because our exams in this class is always going to be open book and open notes on paper, as in some remnant of a tree kind of paper, not e-paper. Okay, because I don't want someone to argue, well, but e-paper is an element of the set of all paper, so e-paper should be fine. I can use this tablet. No. Okay. Yes, go ahead. Well, I guess we don't have enough time to do it today, which is okay. For people who, for whatever reason, is missing today's class, it's okay. Yep. Go ahead. Yes, you have permission to do it. The only thing you cannot do based on that license is to release your version of the note and taking all the credit. Like Iliad made this. Yeah, yeah, yeah. Yes. Yep, yep, yep. Anything that is based on that tree is fine in the exam. Yes. Okay. So did I give you a did I put you into the class? Like nope, not yet. Okay, so okay, can you follow me to the office so I can clean up now so the next class can
Hi.
come in? Hi, yeah.
I got a quick question before leaving. Uh,
Okay. Go
s-
ahead.
yeah, so the second
Go
to the
ahead.
last example we just worked on is false, and the last one is true, right?
Um, so this one is always true, and so is this one. In other
Oh, the
words,
both are true.
they're both true
Okay.
because they are
And
basically
one,
the same thing.
mhm, okay. And one more question.
Mm-hmm.
Uh, as I was saying, like whenever like I'm reviewing this, I'm gonna like review it later. So I know I have to like make sense, like the computer side point of view and then
Mm-hmm.
the algebra point of view. But like when we're working towards the exam, like
Mm-hmm.
how what kind of thing we're like supposed to like see or solve so I can work accordingly.
Oh,
Like I'm kind
okay.
of lost a little bit.
Okay, so the exam is always going to be a problem-solving kind of question.
Mm-hmm.
So that means you really need to fundamentally understand the concept so that you can apply those concepts to solve the problem in the exam.
Okay. So for
At
example,
some point,
mhm,
yeah, go ahead.
go ahead. Yeah. So for example, like if we're like once we clarify these concept, like the one that we worked on last lecture and this lecture, so
Hmm.
basically it's gonna be like, oh, is the statement true or not? Or like something like, oh, can you abbreviate these format to the other format? Something like that? Or
So I will have expression and then ask you what is the result of that expression.
I'm sorry, I can't hear you.
Question to see whether you understand the relations.
Hello?
That's a lot that I'm still talking to the student and then I disconnected everything on my computer. Yeah, I'll zoom the student back on.
Would it save the Zoom file or not?
It is still saved, yeah, but the conversation was cut as a result of that. And I did not intend to cut that conversation yet. So, huh? Yeah, I will post it later. But give me a second because I was still in the conversation earlier. Okay.
Hi. I think I'm
How,
back. Yeah, I don't know where I was lost at. Did you hear certain
okay. Can
part?
I have the conversation after I get to my office?
Sure.
Okay,
Thank you.
because I'm in the process of moving from the classroom to my office.
Hmm. Yeah, please go
Okay,
ahead. I'll
so
wait
give me a
here.
stop again.
Hmm. Thank you.
Yeah, you're welcome.
Mhm.
Yep, the computer is still on, so it's
Yeah, I'll
just
just
using
be
the mic
here.
and the speak
Hmm.
now instead of using my headset.
Do you have office hours at 2:30 or do you do the lectures?
I have technically my office hour is from 8 to 9 today, so this is not even my office hour. But since I have to stay for a meeting at 3:30, so that's why I'm just hanging around, and you guys can hang with me.
What about after 3:30?
After 3:30, I think I should go home.
Okay. Then I'll ask you tomorrow.
Okay. I was gonna ask you last time about this one. Okay, can you wait, please? Sorry, okay. I can ask them. Oh, okay. You can scan it and send it to me? Yeah, take a picture. Okay. Yep.
All right. Well, Ryan is not here yet, so I guess I can continue that conversation. Are you still on?
Yeah, yeah, I am.
Let
So,
me, okay, wait,
uh-huh.
wait. I'm trying to onto my Zoom account on the phone,
Hmm.
so I don't have to use the computer. I'm waiting for the
Okay,
next professor to come in.
sure.
Mhm. Oh, okay. Um,
All
all right.
right.
So
Oh,
I
I
have
have
to
to
turn
turn
off
off the
computer
computer
side.
side.
Sure.
All right, there we go. Okay, go
Yep.
ahead.
So what I was saying is, okay, let's, for example, let's take this class and then last class as an example.
Mm-hmm.
So you know how we're working on this algebraic side and then also like incorporating the computer, I mean science aspect of it to compare and
Mm-hmm.
contrast. So is it
Mm-hmm.
like, oh, we should be able to figure either way around, like in any given situation, and then, oh, if you ask like, oh, in this situation, what's supposed to be in this, I mean, the computer
Hmm.
side, and then solve the question that way, or how are we to think
Um,
it?
I think the first exam is will be more like the examples that we have that I've been working on using
Mm-hmm.
Joplin. So I
Mm-hmm.
will give you an expression, and then you have
Mm-hmm.
to tell me what is the answer to the expression.
Okay, so basically, yeah, it's just trying to like move things around, like, oh, if you are given this situation, you'll be doing this situation kind of thing.
Correct. Yeah. So
Okay.
what I'm really testing is whether one, you understand the syntax of the
Mm-hmm.
mathematical notation, and two
Mm-hmm.
is do you know how to figure out things based on how the set operations are defined. So I can
Okay.
use intersection, union, difference,
Mm-hmm.
subset of, proper
Mm-hmm.
subset of. So I can use all of those operators, and I'll give you an expression that involved at least a few of those operators and notations, and then you have to apply what you have learned in order to give me the answer, because that's what you need to do to figure out the answer.
Okay. And one more, when is our first exam gonna be? Just so, I mean, I tried to
Around
look it
week
in the
6.
syllabus, but I couldn't. Okay,
Yeah.
week
Yeah,
six?
about week 6. It kind of
Mm-hmm.
depends on how quickly or how slowly we
Yeah.
cover the material. So there's
Mm-hmm.
no actual set date, to do the
Okay.
exams. The
Okay.
final exam, on the other hand, is always going to be the
Yeah.
scheduled exam date and also time, based on the final exam schedule.
Okay. So, okay, that's it for now, and I'll let
Okay.
you know if I have any question for next time, and I really appreciate it. Thank you so much. And I'm sorry,
So
like you have to go through like extra steps from in order
no,
to
it's
provide
fine.
me with this. Yeah. Thank you. Bye-bye.